Hello, so welcome back everyone. In this lecture, we will discuss about column designing using IS 13920. So ductile design of columns. Let us look into the codal provisions regarding ductile detailing. So clause number 7 is talking about column detailing. So if you look here, there are figures that are given, and these figures are going to tell you what are the different uh, detailing criterions that we should look into. So now basically the things that we have to look into is, for example, if the axial compressive stress, let me highlight. Okay, so if the axial compressive stress um, exceeds this value, okay, so if the axial compressive stress is exceeding this value, then you will be considering it as a uh, column. So if you look into beam, you will see that the criterion for a beam is the axial load in it should not exceed this particular 0.008 FCK value. And then there are certain minimum dimension values. Again, in case of column, you might be remembering we had preliminary dimensioning. While doing preliminary dimension, we had um, restrictions on the dimensions. For example, the width has to be greater than 200 mm. Similarly, there was L by D ratio has to be greater than zero point 0.3. So similarly, we have minimum dimension criterion here also. So minimum dimension should not be less than 20 times the largest longitudinal bar. So this is one criterion. And the second criterion is over 300 mm. That means the minimum width for a column is 300 mm if we are confirming to IS 13920. Similarly, aspect ratio is also given, just like beam. We have for column, it should not be less than 0.345. That is the aspect ratio. So if it is less than zero point 0.4, then we have to look into requirements of uh, section 9. We will see what is section 9. Then these are uh, criterions relating to capacity design, that is to ensure strong column weak beam philosophy, that is the strength of the beams and the columns, the cumulative strength of the beams and the columns. The capacity ratio has to be greater than 1.4. Okay, that is the sum of the strength of the columns. If you look here at any beam column joint, the sum of the strength of the columns meeting at the joint should be at least 1.4 times greater than the sum of the strength of the beams meeting at that particular point. So that is the idea of strong column weak beam philosophy, to ensure that failure occurs only in the beams, because if columns fail, then it will lead to progressive collapse of the entire building, whereas if a beam is failing, it is only a localized failure. So here that is given in equation format also. Sum of the column moment capacity has to be greater than or equal to 1.4 times sum of the beam moment capacities. Now let us come to the detailing provisions. So first detailing provision that we require is the longitudinal reinforcement. Okay, so the first one is the longitudinal reinforcement. So here how do we it is telling that the minimum diameter of the longitudinal bar has to be 6 mm. Okay, it should not be more than that. Then let's see. So other criterions are regarding the curtailment and the splicing of the reinforcement. Crucial ones are like how should the lapping be provided, that is not more than 50% of the steel bar should not be lapped at any section. All these are similar to that of beams. Okay, so typically the longitudinal reinforcement design is same as that we did in IS 456. That is, we have a moment as well as we know the axial load that is going to act on the beam. Now what we will do is we will find out Pu by FCK BD, and similarly we will also find Mu by FCK BD square. Now we go to the column interaction chart and find the value of percentage of steel required, and then we will provide it uniformly distributed on all the four sides. That is how we do the longitudinal reinforcement design. Now crucial part is the transverse reinforcement. Okay, now in beams, if you remember, we talked about special confining reinforcement. We told that the links has to be 135-degree hook has to be there, minimum 6 mm diameter. The minimum diameter of the link is 8 mm. That also we told. Now, in addition, when it comes to column, we have some more restrictions with regard to the um, links. So let us try to see that. For example, if you see this figure, uh, this dimension, that is the dimension between the two legs of a stirrup, the dimension between the two legs of a stirrup should not be more than 300 mm. Okay, this h is measured ideally between the center to center of the longitudinal bars. That is how we measure this h. So this should never exceed 300 mm. That is one criterion. This is a crucial criterion with regard to the designing of confining reinforcement for columns. So here, if you look here, this column is a large column. For example, this dimension, let us say maybe 600 mm, and this dimension is 300 mm. So in such a case, here this side, the depth between the column, the distance between the longitudinal bars is not greater than 300 mm, whereas in this direction the total depth is 600 mm. So in that case, what we have to do is we will have to do a cross tie in between, okay, so as to reduce this depth between the legs of the the transverse reinforcement or the lateral ties to be kept less than 300 mm. So simply we will provide a cross tie. Similarly, if the dimension in both the sides is greater than 300 mm, in such cases we provide two cross ties in between. So conveniently provide cross ties to ensure that distance between any two legs of the stirrup has to be always kept less than 300 mm. So that is one important part with regard to reinforcement. Then another criterion is, except where special confining reinforcement is provided, the maximum spacing between the lateral ties cannot exceed half the least lateral dimension. So that is, for example, imagine we have a column like this. Okay, we have a column. So basically what it means is, from the support on either side for a length L0, we should be providing special confining reinforcement similar to that of a beam, and in the remaining portion we can provide normal reinforcement as required by the design. However, this normal reinforcement that we are providing, this spacing should not be greater than half the least lateral dimension of the column. So for example, the column is D, this is D, and this is B. So least lateral dimension is B. So this should never exceed B by 2. The spacing should never exceed B by 2. So in this particular region where you are not providing special confining reinforcement, and in this region where you are providing special confining reinforcement, the spacing has to conform to special confining reinforcement. Now the code will say how much is this L0 and what should be the spacing of special confining reinforcement, etc. Let us see. So what the code is saying is, first thing is shear design. So when we do shear design, the shear design has to be done for the factored shear force as per linear structural analysis as well as from plastic analysis, just like we did for beam. However, in case of columns, most of the time we will not be given the results of beam that are spanning into the columns. Most of the time, this value of design shear force will be directly given in the question. Okay, if not directly given, we have to find it out the same way that we did for beams. Okay, otherwise this is the way. Now the idea is very simple, that is the shear force that is going to generate here, we have to find it from the analysis that we did just like for a beam. Okay, but that is not required at this point. Now how to design special confining reinforcement. So first thing is L0. So what is this L0? L0 here, if you look here, L0 should not be greater than the largest, it should not be less than the largest lateral dimension of the column, that is 1. Second is 1 by 6 the clear span of the member, that is 1 by 6 the height of the column. Second is 450 mm. So that is regarding L0. Then second one is what should be the spacing of special confining reinforcement. So one criterion is 1 by 4 the minimum dimension of the member. Second one is 6 times the diameter of the smallest longitudinal reinforcement bar. Another one is 100 mm. So we have to check this. And then there is one more criterion regarding the cross section of the bar. So most of the time we choose fix the cross section of the special confining reinforcement and we find out the spacing. So spacing will be governing this particular equations will also govern the spacing. Now let us look closely into this. One set of formula is given for circular columns and another set of formula is given for, so here the diagram is given. So once everything is completed, you can simply draw the diagram based on this. Now another set of equations are given for rectangular columns. So here if you look, the equation is 0.18 SV. SV means spacing of the longitudinal stirrup, I mean the transverse stirrups or the lateral ties. H means, as I told you, the distance between the center to center of the reinforcement, yeah, between the parallel legs of the reinforcement, that is the lateral ties. Then FCK by Fy, usual notations. Then AG by AK minus 1. AG is the gross area of the column and AK is the area of the column core or the confined core. We will see what it is. Okay, so these are the basic things that are required to solve the problem. So at this point, let us try to see how to design a column with these preliminary things that we have known. We will come back to this and look into the caudal provisions as and when it arises. Okay, so let us try to take up a problem. So here what we will do is, let us consider a rectangular column. Okay, let us consider a rectangular column. So let us say the dimension is 400 by 500 mm. So this is the dimension of the column. This is roughly square. Then let us say the length of the column is 3 meter and let us say it is using M25 concrete and Fe415 steel. Okay, so these are the dimensions of the column. Now the loads, let us say uh, the axial load that is acting on the column, then we have the bending moment acting on the column. We have different cases: dead load, then we have live load, and then we have earthquake load. So in dead load, the axial load, let us say, is 1000 kilonewton, and in live load, let us say it is 800 kilonewton, and here in earthquake it is 550 kilonewton, and with regard to bending moment it is 50 kilonewton meter, 40 kilonewton meter, and in earthquake it is 100 kilonewton meter. And with regard to shear force, let us say the design shear forces, let us say it is 250 kilonewton. Okay, design shear force. Now, as you know, just like in beam, the very first step is to find out the design moments. So design moments as well as design axial load. So as you know, it has to be calculated based on two load combinations. So we will have to consider two load combinations. Wait. So we have to calculate the design forces. First load combination for axial load is PU will be, it will be greater of, first one is 1.5 into dead load plus live load, that is 1.5 into 1000 plus 800. This value is 2700 kilonewton. Second one is 1.2 times dead load plus live load plus earthquake load. So if we do this, we will get a value 2820 kilonewton. So the axial load that we are going to take in for the design will be the greater of the two, that is 2820 kilonewton. This will be our PU. Similarly, next is MU. MU again will be greater of, first load combination will be 1.5 dead load plus live load. So that is going to be 1.5 into 40 plus 50 plus 40, that will be 135 kilonewton meter. Similarly, second one will be 1.2 into dead load plus live load plus earthquake load. So that value is going to be 228 kilonewton meter. So again, the design bending moment will be this value. This will be our MU. And as you know, VU value is given as 250 kilonewton. So first step will be we have to design for the longitudinal reinforcement, and second step will be we have to design for the shear reinforcement. So let us go for longitudinal reinforcement design. Now again, with regard to design load combinations, sometimes directly the value that we have found out, PU, MU and VU, these three will be directly given as the maximum effects of, or the factored effects of the combined effect of earthquake and gravity loads. So these PU, MU and these three will be the, these are the factored combined effect of, or the maximum combined effect of earthquake and gravity loads. Okay, these may be directly given in the question. In that case, our design problem starts from this stage. Okay, so now longitudinal reinforcement. Longitudinal reinforcement is just like that we did in IS 456. So what do? We have to use the design charts given in SP16. So here we require what is known as the um, effective depth is required. Okay, or the distance to the center of the reinforcement is required. So in this case, what we do is Let us assume 25 mm diameter bars. Okay, so let us assume 25 mm 5 as the longitudinal bars, and let us assume a clear cover of 40 mm. Now, most of the time, the forces acting in both the directions may not be given. Okay, so it may not be telling whether the forces that we have got are result of analysis in the x direction or the y direction. And especially in case of a column, if it is a square column, whether the forces given are acting in the x direction or y direction is not going to make any difference because the dimension is the same in both the x and y direction. Same is the case if it is a circular column. Whether the loads are given correspond to the x direction or y direction makes no difference. However, when it comes to uh, a rectangular column, it is going to make a difference. Okay, so when it is a rectangular column, what we will do is we will assume, okay, we will make an assumption that we will assume that the column is oriented along the strong axis. Okay, it is acting along the strong axis. That means the column will be oriented in this fashion. Okay, so if the earthquake is acting in this direction, this will be the bending moment will be acting like this, and the larger dimension will be resisting the bending moment. This will be the orientation we will be assuming. Okay, so this will be the direction of the earthquake force. Shear force will be acting in this direction. Axial load will be acting vertically downward, and this will be the direction of the mu. Okay, and also let us assume. So if we look in this particular fashion, the this will be the dimension of the depth of the column, and this will be the width of the column. So we need the to find out what is d dash. So d dash will be equal to, this is the distance to the center of the longitudinal bar. So that will be equal to the total dimension, that is 500, minus clear cover. So clear cover means it will reach up to the outer edge of the longitudinal bar. Now minus 1 bar diameter divided by 2. So this will be the, okay, so d dash value will be, this will be the d dash value. So this value will be 52.5 mm. Basically what we are trying to find out is, we are trying to find out this. So for example, here we have two bars. We are trying to find out this distance, d dash. Okay, so that is clear cover plus 1 bar diameter divided by 2. Okay, cc plus 5 by 2. So that is what we have found out here. Now we need to find out d dash by d, d dash by capital D. So that is 52.5 divided by 500. We will be getting 0.105. So this is approximately equal to 0.1. Okay, so the chart we have to choose will be corresponding to 0.1. D dash by D is equal to 0.1, and then Fe 415. Now we also need to find out Pu by FCK BD. So Pu divided by FCK BD. So that is 2820. It is in kilonewton. We are converting into Newton, divided by 25 into 400 into 500. So we are getting 0.564. Similarly, mu divided by FCK BD square. So that is again 228 into, here we have to convert in Newton mm. So we multiply by 10 raised to 6 into 25 into 400 into 500 square. We will be getting a value 0.09. We may take it as approximately 0.1. So if we go to SP16, we have the interaction charts are available. So if we go to chart number 44 of SP16, okay, chart 44 of SP16. So we are assuming the reinforcement equally distributed on all four sides. Okay, so this is the case we are taking. So if you go to the interaction charts, we will get the value of PT. We can get the value of PT as uh, percentage of reinforcement rho. We can get it as 3%. So 3% of reinforcement is required. So let us find out the AST that is required. So AST required will be 3 divided by 100 into B into D. B is 400 and D is 500. So 6000 mm square is the AST required. Let us provide 8 numbers of 25.5 and 8 numbers of 25. Okay, so this will amount to, if you do the calculations, you will see that this amount of reinforcement is 6441.2 mm square, which is greater than required. Okay, so this will be the reinforcement that we will be providing as longitudinal reinforcement. So that is the end of longitudinal reinforcement design. So if you try to draw a figure, so here I have arranged already 1, 2, 3, 4. So if you look how do we do the arrangement? First what we will do is we will arrange 4 bars at the 4 corners. So 425 bars are arranged at the 4 corners, so that will make 425 bar. Then at the middle we will arrange another 4 set of bars. So 28 bars are now all the 25 mm bars are arranged. Now what we can do is we can arrange the uh, 20 mm bars. So here we can provide a 20 mm, then another 20 mm can, so another 20 mm can be provided here. Like that, let us provide 120 mm can be provided here. So another 20 mm here. So this is how we will provide the bars. We have 8 20 mm bars as well as 8 to 25 mm bars. So in this way we can provide the reinforcement. Okay, and what is shown on the outer is the link. Now next is we have to go for the shear design. So with regard to the shear design, again, in the problem, sometimes directly the longitudinal details of the longitudinal bars also will be given. So if the details of the longitudinal bars are given, then our design will start from the shear design only. We don't have to do the longitudinal bars design again. Okay. So let us do the shear design. So here directly we have the maximum design shear force that is given. VU is given as 250 kilonewton. So now once it is given as 250 kilonewton, now what we have to do is we have to do the shear check whether it is satisfying the design shear strength of concrete, and then if additional shear reinforcement is required, we have to provide the stereo spacing everything accordingly. So let us try to see. So if you look here, VU is equal to 250 kilonewton. So first thing we have to find out is we need to find out tau V. Tau V is equal to VU divided by B into D. So we have to find out the effective depth. So how do we find out the effective depth? So if you look here, effective depth can be found out from this particular figure. So if we say this is the center of the central axis is this. So one area is compression area, other area is tension area. So effective depth will be, let us say this is the compression area and this is the tension area. Effective depth will be distance from the outer compression to the this portion, center of this particular, this set of reinforcement. So this will give you the effective depth. So to find out the effective depth, what we are going to do is we will be calculating the total depth d minus 40 minus 25 divided by 2. So that is going to be the effective depth. So for the time being, let us say we are ignoring these reinforcements and their contribution um, to the tension. Okay, so we will take this as the effective depth. So if you look 500 minus 40 minus 25 divided by 2. So that is 500 minus 52.5. So it comes around 447.5. So if we calculate VU divided by BD, it is going to be, it is going to be 1.39 Newton per mm square. Now if you know this is less than tau C max for M25 concrete. Tau C max for M25 we know, if this is tau C max and this is the grade, this is 20, 25 and 30. So we know the values 2.8, 3.1 and 3.5. So this value for M25 is 3.1 Newton per mm square. Now what we have to do is we have to find out the design shear strength of concrete. So to find out the design shear strength of concrete, we require the percentage of tension reinforcement. So what we do is we will assume that half the reinforcement that is provided is the tension reinforcement, because if you look into the uh, column, we have reinforcement equally distributed on all the four sides. So one area is the tension area and another area is the compression area. So whatever reinforcement that is coming in this region, we will assume that as the percentage of tension reinforcement. So the percentage of tension reinforcement PT will be equal to half of AST divided by BD. So that will be equal to half of AST that is provided, we earlier calculated, that is 6441.2. Okay, this is the AST that is provided, divided by B is 300, D is 447.5, multiplied by 100 to convert that to a percentage. So this value will come out as 1.79 percentage, that is roughly 1.8 percentage. So now we can calculate the design shear strength of concrete. All that we have to do is we have to go to SP16. I think it is table 61, which is for shear, table 61 of SP16 I think. So if you go to this particular table, table 61 or table 60, so we can calculate the value of tau C as 0.79 Newton per mm square. Okay, tau C we will be getting. Now we want to find out what is the shear force that has to be resisted by the stirrup, VUS. So VUS is equal to VU minus tau C BD. So that will be equal to 250 minus point. Again, in compression members, the design shear strength of concrete can be further enhanced. Okay, so IS 456 gives this particular formula, that is delta is equal to 1 plus 3 PU divided by AG FCK, and this has to be less than 1.5. Okay, so this is the factor for enhancement of the shear strength of concrete. So let us find out what is delta. Delta will be equal to 1 plus 3 into, this value is 2820 into 1000 divided by AG is the gross cross-sectional area of the column, that is 500 multiplied by 400 into FCK is 25. So this value comes out as some 2.69. So this is less than 1.5. So we will be taking the value of delta as 1.5. So which means we can enhance tau c. Tau c modified will now be equal to 1.5 into 0.79. So that will come out as some 1.19 Newton per mm square. So that will be the modified shear strength of concrete. Now the shear force that has to be resisted by the stirrup, that will be equal to Vu minus tau c BD. Here we will take the modified value. So that is 250 minus 1.19 into B is 400 and D is 447.5. This will be the values. So we'll be getting a value 37 kilonewton. So a small value is coming as the force that has to be resisted by the stirrup. So this again, I think it is from table 62. We can get the stirrup spacing required, SP16. So we have to find out VUS divided by D. So that is 37 kilonewton divided by 44.75 centimeter. So we will be getting some 0.83 kilonewton per centimeter. Let us assume 10 mm 5 stirrups. So 10 5 FE415 stirrups if we are assuming. So the spacing that is required here will be very large. We are getting some 450 mm as the spacing that is required. And you know the spacing is extremely large and this cannot be provided. So the spacing as per shear reinforcement is only very nominal. Nominal reinforcement is only required. Now sometimes in the problem, the maximum design shear force also will not be given. Rather, it will be told that the design is governed by nominal shear reinforcement. That means the shear design, whatever design is given by nominal shear reinforcement. Or even you may, if the shear design is not explicitly given, tell that you are assuming that the uh, the shear design is required is only nominal shear reinforcement. So in such a case, what we have to do is then we have to look for the confining reinforcement. That means the design is now going to be governed by the confining reinforcement. Okay. So now if the problem directly gives you details of longitudinal design, okay, this detail is directly given to you. Also the details of shear design is directly given to you. Then the problem is going to start. The only thing that we have to do will be the special confining reinforcement. That is the ductile detailing as per IS 1390 will only have to be done by us. Whatever we did till now will not have to be done. Okay, so let us see how to do the special confining reinforcement design. So here, first thing that we need to do is, as we know, this is the column. The length of the column is 3 meter. We want to know what is the distance from either end, L0, up to which special confining reinforcement has to be given. So these are the regions of SCR. Okay, so we need to decide that first. So first one is L0. So as you know, L0 is equal to it is going to be the greater of three things. First one is going to be the largest lateral dimension of the column. So largest lateral dimension of the column, as you know, we are taking it as capital D, the largest lateral dimension of the column. So in this case, we have a column 400 by 500. So we will take it as 500 mm. Second one is the 1 by 6 of the clear span of the member. 1 by 6 of the clear span of the member. So clear span of the member is 3000 mm. So 1 by 6 of the clear span of the member is again 500 mm. And third one is 450 mm. So of three, the greater value is 500 mm. So the value of L0, that is the region up to which we have to provide special confining reinforcement, is 500 mm. Okay, in the remaining region, the spacing should not exceed the smallest longitudinal dimension divided by 2. That is, smallest longitudinal dimension is 400 mm, divided by 2 will be 200 mm. Okay, the spacing should not exceed 200 mm in this region, whereas in these two regions L0, we have to, it will be governed by special confining reinforcement. Now again, let us choose the dimension of the special confining reinforcement as 10 mm 5 stirrups. Okay, so let us choose 10 mm stirrups. Now we have to decide what should be the spacing of these 10 mm stirrups. Now before we go to the find out the spacing of the 10 mm stirrups, let us look into how this can be arranged if you are providing 10 mm stirrups. So as you know, if you look here, the dimension here is 400 mm. Okay, that means if you go for center to center of the bars, this will be greater than what we know as this will be greater than 300 mm. So the code says in no way the distance between the legs of the two parallel legs of the stirrups be greater than 300 mm. So in that case, we will have to provide cross ties. So here we will have to provide one cross tie here. Okay, one cross tie will have to be provided here. Similarly, we will have to provide one cross tie here also. Okay, one cross tie will have to be given here also, just to ensure that the total distance between the two bars, okay, this distance should not be what we are doing. It is we are trying to ensure that this distance that we are having, distance between these two bars, center to center of these two bars, is not exceeding 300 mm. It should not be greater than 300 mm. That is why we are providing cross ties. So when we are providing cross ties, it will be something like this. Okay, and this will be the main stirrup. So we have this outer lines are the main stirrup. In addition, we are providing cross ties also. Okay, and this distance will be the h. Okay, the h that is going to be used in the equation will be the center to center between these two parallel legs of the stirrups. Okay, the largest of these two. That means this is also h. So for example, this distance is also h. However, we have to take the largest of the h values. Okay, so we will try to see how that has to be found out. So let us calculate that h value first. So let us say the total distance from the top to the outer of the longitudinal bar is whatever that is total minus 40. So from 500, if we subtract two covers, okay, from 500 if we subtract two covers, the distance that we are going to get is